Thanks for being here. I'm really honored that I was chosen to be a Löwdin lecturer. And as you can see, my talk, the title of my talk is, have you ever pulled on a molecule? So have you? So, oh, super. So you need to explain more about this. Yeah, so I was about to do this. I mean, of course, you can do things like this, right? But you don't pull on a single molecule, right? This is a problem. Before I continue, who is a chemist in the audience? Okay, hands up. Who is a physicist? Oh, okay. Okay, thanks. So by training, I'm also a chemist, and I started in experimental chemistry. Then I was, some 25 years ago, I was pretty much unsatisfied with the explanations that I was given for certain effects. And so I became a theoretical chemist until I realized that I need to dig more deeply into physics. So I would consider myself also a physicist, I guess. But my heart still beats for chemistry. And so, you know, I really wanted to pull on a molecule. Have you ever asked yourself why there are hardly any books on popular science books on chemistry? I mean, you find popular science books on physics, right? Astrophysics, Big Bang, biology. Where do we come from? Where do we go? But there's hardly anything in chemistry. And why is that? So I think it's because we talk about a subject that nobody can really see, right? So you can't see the molecules. And it's super hard to make up your mind. We have our own language. It's super hard to explain the language to somebody who has not studied chemistry, right? And when you think about describing all these objects in physical terms, it's getting even more complicated. And that is, I think, one of the reasons why we don't have popular science books on chemistry and why it's so hard to discuss chemical subjects with people who are not really into chemistry, right? Although we are all chemistry, right? I would consider myself a really complicated reaction network, right? So I'm full of chemistry, and still this is not a matter of discussion among people, right? And I think the reason for this is the fact that we don't see our objects. And because we don't see them, it is hard to touch them, or a single one of them. Of course, I can touch a huge number of them by just pulling this piece of paper up. But if I can't do that, I will have a hard time pulling on a molecule. But I would really like to know how it is to pull on a molecule. And so theory is actually the only option that we have, because we have a theory that explains the molecular world to a degree that has never failed us, right? That's quantum theory. So the question is whether we can exploit quantum theory and naturally in some sort of virtual reality environment to pull on molecules. And that will be the topic of my talk here. But before I do that, of course, I'd like to relate what I did to what Löwdin did. And you saw Roland's list, you know, the natural orbitals, the Löwdin orthogonalization, you name it. And of course, that is kind of the bread and butter of our daily life. And so I went on and I've tried to figure out whether Löwdin actually had a relation to E.T.H. Zurich, and he had. And that's kind of embarrassing for E.T.H. Zurich, I would say, because as you can see on my next slide, Löwdin and E.T.H. Zurich. This is from the paper that Roland mentioned by Erkki Brenders, because Löwdin was actually for 6 months a postdoc with, a student with Wolfgang Pauli. And Pauli is actually known for his harsh comments, and Löwdin also suffered from that, I guess, as you can see here. So this experience working in 46 with Pauli made him the founder of the field of quantum chemistry as we know it, because in a negative way, because he didn't want to do the physics the way Pauli did, right? And so Brenders writes that they were very different personalities indeed, and they did not click. And there are many examples next to this one, when Pauli visited Uppsala in 58, seeing Per-Olof Löwdin and saying, Löwdin, how did you succeed to survive in physics? And then he said, I was promoted to a chemist. Fortunately, I started as a chemist. And reading the text is really interesting. I realized that he was writing about another Swede. Like, it is quite remarkable to note that another Swede, Carl Erik Fröberg from Lund, was visited Pauli the same year. While Löwdin became the first professor in the new discipline quantum chemistry, Fröberg initiated and developed numerical analysis in Sweden, becoming its first professor in Lund 1965. And now the interesting thing is, when I started working on my PhD, which was in numerical solution methods for atomic structure physics, it was Fröberg's book which I used to learn numerical analysis. So that's the world is really small, right? And I strongly recommend reading this paper. Okay, let's get back to our topic. So the idea is to realize a virtual reality setting in which we can interact with molecules in a way that it's physically reasonable, so that in a way that is fully covered by quantum mechanics. Before I delve deep into this, let me first review what we actually do in quantum chemistry. So applied quantum mechanics to molecular physics or chemistry. And that is, we usually talk about structures. And that is within the Born-Oppenheimer approximation. So almost all of our thinking wouldn't work without the Born-Oppenheimer approximation. Without the Born-Oppenheimer approximation, there wouldn't be any potential energy surfaces. And of course, quantum theory does not need this approximation, right? And if you have a full quantum solution of a molecule without the potential energy surface that comes into the game through the Born-Oppenheimer approximation, it will be very hard to talk about the ordinary concepts of molecules, like molecular structure, because suddenly you don't see a molecular structure. But we adopt this Born-Oppenheimer approximation every day. So we put in the molecular structure into the game, and then we assign an energy to this molecular structure, and that we do through the electronic Schrödinger equation, which you can see here, right? This is the electronic energy, the electronic wave function, there's the electronic Hamiltonian operator, and this energy actually gives us a potential energy surface for some given molecular structure. And of course, from the outset, we don't know the structure. So we need to find an optimum structure which resembles our molecule in some way. And that means that we start with some structure, we solve the equation, we get an energy assigned to the starting structure, and then we also know the forces on all the atomic nuclei in that structure, because the forces are given as a negative gradient of the electronic energy. And then we can apply structure optimization to minimize the forces, and we arrive at a structure which is chemically meaningful, right? But the point is that we start from structure, we get an energy, and the energy allows us to access properties, molecular properties, and eventually function. So function that these molecules perform. Of course, the equation is terribly complicated, right? So this is, again, the same equation, the electronic Schrödinger equation with the electronic energy, but the Hamiltonian is actually of this form. And it's a high-dimensional partial differential equation of second order. It's scary, right? Not only because of all the derivatives that sit here, but also those of you who are experts in quantum chemistry, they know that these terms actually create a lot of problems. The nice thing about it, we know our Hamiltonian exactly. I mean, this is a non-relativistic view. So if you take the speed of light to be infinite, this is the exact Hamiltonian. And there is no way to write an exact Hamiltonian other than referring to elementary particles, like electrons and, in our case, atomic nuclei, because we don't have the energy to split the nuclei, right? Because in that case, we know that all the interactions are given by Coulomb's law. There are no magnetic effects, no retardation effects, because we have set the speed of light to infinity. So this, in this limiting case, a non-relativistic limit, and this is the exact Hamiltonian. And so we know exactly what we do. We can promote this to the relativistic frame, and that was done by Dirac in 1928. And this is what Dirac wrote in 1929, a year after the discovery of his equation, which is Lorentz covariance, so which even fulfills Einstein's special theory of relativity. He wrote, and this is pretty famous. Actually, I think the first part of the quote is more famous than the last one. So let me read the first part of it to you. The underlying physical laws necessary for the mathematical theory of large part of physics and the whole of chemistry. And eventually this turns out to be true. If you're interested in an accuracy which is not extraordinarily high, then this is absolutely true. Are thus completely known, and the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. And then he continues, and this is often, the quote stops here, but he continues saying, it therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed. And that's basically what we do in quantum chemistry, right? And this is wishful thinking, which can lead to an explanation of the main features of complex atomic systems without too much computation. And unfortunately, this turned out to be not true, right? It's a pain, all these computation. Actually, the first talk that we heard today gave you plenty of examples how difficult it actually is. So we had the founding people of quantum mechanics, some of them here, and in the 1920s, 1930s, and it took decades until we had tools available that could be used on a routine basis. And this is basically where we are now. And that has also this situation, the fact that it's so difficult to solve the equation, also has shaped our view on how we consider doing quantum chemical calculations. And I would like to challenge that view in my talk here. Our tools are, of course, supercomputers, and these are some data from 2014. In my group, we run a cluster of 2,000 cores, probably now it's 3,000. There at ETH, there was a central high-performance computing facility with another 20,000 cores. And if this isn't sufficient, you can, in Switzerland, go to a high-performance computing facility, which is called in Switzerland CSCS. And here you see one of CSCS latest clusters, which was in 2014. So we need a lot of computing power, right? Now, what do we do with this? So remember what I said earlier, we need to come up with a structure first, right? And you have seen in the first talk today that these structures can be terribly complicated. But I would like to focus on chemical reactivity. And reactivity is usually a very local effect. And that is the reason why we have multi-scale approaches where we focus with a quantum mechanical region on that part of the molecular system, which is reactive in a sense that you see chemical reactions going on there. And then there is some spectator environment, which can, for instance, be modeled by classical mechanics. And maybe around that there are other dielectric effects that you can model through a continuum. Right? And this is a typical multi-scale approach that we look at it. But chemical reactivity is usually local. So that basically means that you need a few hundred atoms to capture it, to describe what's going on. And of course, many people know this, but I think it was mostly Per Siegmann and Fahmi Himo who actually always pointed out to this fact, that this is possible, that you can understand, even in a complex system, the reactivity if you focus on a few hundred atoms. Okay? And of course, you would like to include some sort of environment, because there could be some dielectric effect that you should not ignore. But in the end, the full quantum mechanical treatment really needs only a few atoms. Let me give you one example. This is from our own research. And we have a couple of these examples. I picked one, and that was our work on hydrogenase chemistry. What do you see? There are different classes of hydrogenase enzymes. This is one. It's the iron-iron hydrogenase. It produces hydrogen and has therefore been considered in, as a means to produce molecular hydrogen through bioengineering ways or electrochemical pathways in technical applications. And there's also a strong hydrogenase research group here at Uppsala University. So this is how the protein looks like. You see embedded in here is a metal cluster, that's the active site. You see this is the enlarged structure of the active site. In yellow, these are sulfur atoms, and in brown, these are iron atoms. And so there are 6 iron atoms. From an electronic structure point of view, this is a nightmare. Okay, and so what you can apply, these days, what people start to apply to it are actually wave function-based methods. And it becomes feasible, but it is not at all routine. What is routine for these calculations is DFT, okay, and especially broken symmetry DFT. Broken symmetry DFT, from its foundations, is fine, apart from the fact that the exchange correlation function could be a problem to accuracy. But otherwise, it's a well-defined theory. So we applied broken symmetry DFT to this system. And of course, you would like to understand what can happen, what kind of chemistry can happen there. Of course, hydrogen production. But at that time when we worked on this, people were worried about molecular oxygen. Because the moment this system sees molecular oxygen, the cluster decomposes and it's dead. And if you want to apply it in any technical application, you need to make sure that it's stable against oxygen, right? And so we tried to figure out what is actually going on. You see, again, this is the active site here, here in a kind of Lewis structure model. And oxygen comes in as triplet oxygen and is somehow converted to reactive oxygen species, like H2O2, the OOH radical, right? OH minus, singlet oxygen, and so on. And you have various places where these reactive species can actually start destroying the cluster. And if you want to figure out what's going on, because experiment is not giving you the full resolution picture here, you need to do calculations. But what is then the charge state of the system, right? It's a combinatorial explosion of parameters that you need to consider in the calculation. So you have different model sizes, you have these many reactants, then you have different protonation states, protonation sites. There can be numerous intermediates. You have various charge states. Spin states can change. You need to look at all of them. You need to make sure that in these clusters, because it's broken symmetry DFT, that the local spin distribution is reasonable, right? And you have conformational effects. And all of this needs to be combined. It's a combinatorial explosion, so that you need to look at thousands of structures. And to do that manually, it's really a pain. And my PhD student did that. And I felt very sorry. All I can say is I'm not giving any topic to my PhD students that I'm not willing to work on myself. So I did this too, but some 15 years ago. I know what kind of pain this is. But Marta Brusca and Arndt Finkelman, they really did that. They looked at all of this. But seeing this, again, knowing, because I did pretty much the same work some 15 years ago on a nitrogen fixation system, that you don't want to do this. It can't be that a single human being needs to spend 3 months, 3 months would be cool, 3 years of a PhD to work on reaction mechanisms at such a system. There needs to be a different way, right? And so we started thinking about these new different ways. And that was basically in 2014. So I've stopped almost all my computational chemistry activity until we have a new system which allows us to do such calculation in a different way. Because this is what we do now, right? You see, the button presser, fancy portrait of the man of the future, Walter Crane, 1907. This can't be our future, right? But this is what we do. We have a keyboard and a mouse, and this is what we do as computational chemists every day. So let me, for those of you who have not done so many calculations, actually, let me elaborate a little bit more on the actual protocol in how we elucidate reaction mechanisms in quantum chemistry. Usually we rely on Eyring's absolute rate theory. And of course, there are issues here, and you can improve on it, and so on and so on. But that is not the topic here. It's not decisive, right? But eventually, you have some reactants. You are looking for some product. There will be a transition state in order to get the kinetics right. You need to know what the barrier is, right? So what you do is you find local minima on your potential energy surface, which is defined by the electronic energy, right? And you look for the saddle points. To optimize the local minima is not that difficult. The saddle points is a different story. That's what you do. And it's a pain to do that, because these are the steps. You set up guess structures for these set local minimum and cell point structures, right? You start local optimization procedures in order to get all the forces down. Then you get some results. You look at the results, figure out, does this make sense chemically? Then if it doesn't, you repeat. And those of you who have optimized transition states know that it's a pain, because you can, it's hard to converge them. You look at transition states that are irrelevant, and then you know that you still haven't found the right one, and so on. The algorithms strongly depend on the good guesses. Failed optimizations provide only little information for new searches, and it's exhausting manual work. But when you look at it right away, you know that something is wrong, right? You can't easily interact with your system. Right? You know it's a structure. You say you look at an optimization towards a transition state, and you see, well, if I just could move this away, because I know I would find my structure I'm looking for. But you can't, and this is a problem. But there's no reason why you shouldn't be able to do that. So it's a trial and error search on a potential energy hypersurface given by the electronic energy. And of course, the picture is it's oversimplified. The reaction coordinate is high dimensional, and it's just one cut through this high dimensional plane. And I like to compare the situation with, say, this is the city of Zurich, and that is the lake of Zurich. These are the Alps. You are standing at the lake of Zurich, and the goal is to find the least exhausting way to Milan by just looking at the Alps. Which way would you take? This is basically what we are doing, right, when we elucidate reaction mechanisms. And actually, it's much worse, because usually you have only local information, so you don't see the Alps. How do you find your path through this? And on top of these conceptual problems that we only have the local information, there are technical problems, like our capabilities of manipulating the structure. They are limited, because we have at most two-dimensional input devices, a mouse, right? But we are talking about three-dimensional structures. Then data interpretation can be a problem, because we have huge amounts of unfiltered data on reaction paths, and we need to be able to isolate relevant information. Then we have a separation issue. It's a technical issue, because often it's different programs that can do different things for us, and that makes the whole analysis really complicated, right? You would like to have everything in one program. And then, of course, we have the long calculation times. So what does that mean for the future? And this is my take on it. Okay, so first of all, we need to get the calculation times down. And basically, this has led us to interactive quantum chemistry in real time. I come back to this in a minute. And that allows us to really interact with the molecules, to pull on a molecule. You will see. I mean this literally. Of course, we would like to have more intuitive and simple man-machine interaction devices. Keyboard and mouse, they are really not most suitable. In principle, we would like to be able to think about the reverse direction, because usually we know what we expect from our molecular system. Right? For instance, if I want to have a catalyst that produces H2, I want a reaction that produces from some chemicals H2, right? So I usually know the function. I would like to know the structure that does the trick. But the ordinary path is from structure to function, and that has to do with quantum mechanics, of course, with the fact that we need to look at expectation values where we integrate out all dynamical degrees of freedom, and suddenly they're gone. And of course, you can already anticipate that if you want to have fast access to quantum chemical results, so fast methods, that you need to compromise. And compromising is fine as long as I know what I'm doing. So we need ways to automatically get reference data, and for that we need an electronic structure approach which is as flexible as possible. So it must be a multi-configurational approach, and we focus here on the density matrix renormalization group. If you like, that is a variant of the CAS SCF approach. So we need a tailored environment. One program for everything: structure, manipulation, calculation, and analysis. And actually we would like to experience the response in real time. Right? The calculation should be really fast, because I just want to manipulate the structure, see what I get, and decide right away, no, this is not the right way, I change the structure in another way. And that means that you won't have time to look at complicated output from computer programs. That's what we usually do. Right? But if you can do that, you can anticipate that you will have a new level of chemical intuition. So we thought about whether it's possible to do quantum chemical calculations in real time, which we call real-time quantum chemistry. So this is not about dynamics, it's about you perceiving the results in real time. So the definition could be something like this, that real-time quantum chemistry is the very fast calculation of, say, the energy and the gradient in such a way that the operator experiences the information flow without any time delay. Okay, that's the goal. Because then I can really talk to my system in real time in a virtual environment. What kind of quantities will be important for that virtual environment? Well, of course, the structure, but also the gradients. So the negative derivatives, because that tells me something about the forces on the atoms in the system. The forces are kind of a descriptor. Okay? The structures you can represent in ball and stick representation. The forces on atoms you could represent as arrows, and you will see some pictures there too. But looking at the pictures really doesn't tell you something about the force. It would be much more convenient to feel the force. Right? You get an immediate sensation about what happens to your molecule, and that's what I mean by new chemical intuition. And of course, you need to visualize in real time important quantities like electron densities, molecular orbitals, isosurfaces, things like this. Okay, this is the setting that we have. So we have a virtual laboratory where we can manipulate our molecules. We have a hardware device that allows us to do more than what a keyboard and a mouse does. And we exploit, for instance, a tactile sense. If I really want to pull on a molecule, well, I need such a device. It's a so-called force feedback device. It's an input device, right, which allows us to change the structure of our molecule. You see, it's like a pen. It's really like a pen. With a pen, you can grab an atom in your molecule and manipulate it, change the structure. Right? The way you do this change, whether you do it quickly or slowly, depends on what kind of chemistry you see, because as you will see on the slides to come, we have a running, in the background, we have a running structure optimization, which always relaxes the structure. So now, if you pull slowly, since you manipulate only one atom in a molecule, the whole molecule will follow. Okay? If you pull quickly, you break the bond. And it depends on what you would want to do in the virtual environment, whether what you will do, whether you will move the pen quickly or slowly. Right? There are electrical engines here that give you feedback on the force. So for instance, if you try to push two parts of the molecule on top of each other, then the pen will push back if the molecule doesn't like it. And the information for this comes from a quantum chemical calculation. So it's a real quantum force that pushes the pen back. And at the same time, it's a three-dimensional input device to change a molecular structure. we looked into this already in 2008 for a simple system just to see whether it's feasible at all. And here we used a pre-calculated interpolated surface, and that was we worked with a proton and explored reaction channels on how it interacts with a single water molecule. And since it's 10 years ago, and of course we have made a couple of advances, and we can do much more, as you will see on the slides to come. When you think about hardware devices and where they come from, then you might have seen this already in the news and some newspapers, that there are actually very many devices available. This is the kind of machine that you've seen before, the force feedback pointer device with all this electrical engine, and this is a pen. But of course you can think about exoskeletons, right? And more of them are becoming available at a cheap price. Or you can think about systems like this, like the Leap motion controller, which figures out where your fingertips are, and then you can use that information to change the structure of your molecule, right? And see, this controller is that device over here, costs $100. That's really cheap. And I think we will benefit in the future from the gaming industry, because they will come up with all these devices, and they will be commodity devices, cheap to buy. This machine, by the way, costs around $2,000. Okay, still, it's not that cheap. It's not really cheap, but it's not really expensive either. The reason for that is they use this in telesurgery, for instance, to train surgeons. Okay, what are the constraints for using such devices? I mean, we are used to the screen, right? And we have a 20 Hertz update frequency, and that is not too high. For the tactile sense, you need to have an update frequency of 1 kilohertz. And if the physical simulation that needs to keep up with this 1 kilohertz update rate should provide all the information on at that frequency. That basically means that you have to run a quantum chemical calculation every millisecond, which is kind of crazy, you might think, right? But remember that I'm talking about a few hundred atoms only for chemical reactivity studies. So our system is, if we talk about chemical reactivity, is kind of limited in size. And so what we expect to develop is a quantum chemical system, quantum chemical method that is fast for a limited size of a system. You can play various tricks, and you can increase this number to, I would say, 100 milliseconds. But you need to run a calculation in 100 milliseconds. Because the response needs to be faster than the manipulation. Of course, you also need to run structure optimizations, otherwise you would create highly artificial structures, and the data will be provided on the fly. I already anticipate that this requires an approximate electronic structure method, and Kohn-Sham DFT would be great, but it is not easy to run such calculations with Kohn-Sham DFT. And so what we usually do is we refer to semi-empirical methods. I will tell you more about this in a minute. Because it's fine to use them as long as you know when they fail you, right? So we need to figure out how to do that. The only thing we expect is, because we use this for structure exploration, that these approximate methods give us the right position on the potential energy surface of the stationary points, right? I want to find my transition state structure basically in the same region where the real transition state structure optimized with a proper method would be. Because then that is a way to really explore structures for chemical reactivity studies. So is this feasible at all? These are some calculations that we did in 2012 with the TurboMode program package. You see it's an SN2 reaction. The setting is okay, not really great, because you see the basis set on hydrogen is really small. But in general, these split valence basis sets with polarization functions are pretty good. And of course, we played a trick. We used an ECP to get rid of some of the core electrons. And you see, these are some structures along the reaction path. You see the wave function calculation takes with turbomole 400 milliseconds. The structure optimization 2 seconds. So you push one. I think this is chlorine. You push chlorine on top of this molecule, and then of course also the hydrogen atoms here react, and that requires then 2 seconds to take that into account. But you see, with a standard package, these calculations are fast. Now you can say, well, but this is a small molecule. Right, this is a small molecule. We want to look at molecules which are 10 times larger. But at the same time, this is just a standard computer program, right? It has a huge overhead. It does things that you must not do in a truly interactive setting. come back to this in a second too. This is another result, another example. This is bromine interacting with ethene. Basically the same setting. Now the system is a little larger in terms of electrons, and that's why you need for a wave function calculation a second, and for the structure optimization 11 seconds. Okay, so it is feasible, but it requires a paradigm shift, because all our technical developments so far have focused on looking at larger and larger systems, right? And so we have linear and sublinear scaling methods to deal with this. But these methods come with a prefactor that is large. And in an interactive setting, you can't have this, because interactivity means you need your result now. There is no way for initialization, right? So you need to restructure computer programs. And that's what we did. We wrote a computer program that is tailored to do this. Okay, because we looked at all these essential steps: basis sets, fog matrix calculation, density matrix construction, iterative convergence in the self-consistent field procedure, subsystem approaches, because we limit ourselves to a few hundred atoms, but there's the rest of the environment, and we want to keep this, we wanted to consider this as well, and specialized hardware. Well, we haven't done a lot here, because we think that all the other things are more important, and we can always, what we do here, we can always port to a proper hardware later on. The most severe bottleneck actually from the list is the self-consistency bottleneck. The fact that we have iterative solutions for the orbitals, and that you never know how many iterations you need. And now you need to consider there's an operator who changes the structure somehow, right? And the structure might be totally odd. And none of the standard optimization schemes that we have is actually tailored for this, because they assume that you provide some sort of reasonable chemical structure. If you provide something which is just strange, then it will be very difficult to optimize the orbitals. But that can happen in an interactive framework. Like, imagine you pick an atom and you pull it here, and suddenly you have a structure which chemically makes no sense. And then it will be difficult to get the orbitals. So we had to think about this. And we did. And you can improve on the self-consistency issue a little bit. But the principal problem does not go away. And here you see another example. That's from Todd Martinez's group, published in 2015. And Todd has a DFT program that runs on GPUs, so on specialized hardware, which is tailored to produce results very quickly. And what he did is he looked into steered ab initio molecular dynamics. So these steered molecular dynamics concepts are around for, I don't know, say 20 years. They have been considered a lot in Klaus Schulten's group with force fields. And of course, force fields are easy to evaluate. It's not a quantum mechanical simulation. And the stimulus to do these calculations, to do such kind of molecular dynamics simulations, I think was twofold. First of all, it allows you to interact with your system, right? Schulten has one example where he looked at an aquaporine, at a water channel in a cell. And of course, it transports water from the outside to the inside of the cell. But when you look at this, you have to look at for a long time until you really see a water molecule crossing the membrane, right? But if you could just pull it, then you see the process right away. And then in '97, there was a paper by Jasinski, which became famous. It's a paper for Jasinski's theorem, which tells you that if you have a steered process for where you have a work or force acting on the system, then the work that is exerted on the system in this non-equilibrium process can be related to the free energy change for the equilibrium process. So it tells you, you pull, and from the energy that you need for this, you can get the free energy of the equilibrium process. It's a really cool theorem. Comes with a problem that you need to pull very slowly, right, in order to have the proper sampling. But I think that was a stimulus for steered molecular dynamics. And now Todd considered doing it the electronic structure way, which is super complicated because these calculations are so important, so expensive. But since he has the TerraChem program, which runs on GPUs, he gave it a try. And then he, of course, observed that for strongly distorted geometries, because you have user input now, hundreds of FCF iterations are sometimes required. Even worse, the SCF calculation may diverge, causing the entire calculation to abort. For pathologically long MD steps, such as those requiring many ADIS iterations, the display trajectory is frozen and haptic input ignored until the MD step completes. And that's of course not possible. You must not do this, and immersion goes completely away. You must not allow the system to freeze. because then interactivity is gone. And of course, we had a similar problem. Our solution to this is what we call a mediator strategy. Now we introduce a surrogate potential from which we actually evaluate the force. And the surrogate potential is updated every time we get new orbitals. And that allows us to quickly get the forces to the haptic device, but it also says if SCF convergence is slow, then it will not allow the user to leave the trust region. And it will not break the immersion, because you still can manipulate your system as long as you're in this trust region. And that works pretty fine. Embedding approaches, when you say you have this implementation, of course you want to include an environment, and so you have to think about embedding, and for sure we did. Currently we consider QMM embedding, but we also consider QM embedding, and for that we have recently published a paper it's JCP, Journal of Chemical Physics. And that is a general approach on embedding. It separates basically the Fock matrix, and we realized that this approach relates to other embedding schemes proposed by Tom Miller and Fred Menby, and even to the separation of electronic and positronic state in electronic structure theory, in relativistic electronic structure theory. And I think this is a way to go for us to have embedding into a large environment. Specialized hardware, well, I already mentioned Todd's work from 2008, 2009 on graphical processing units. Of course, you can parallelize your calculations, and in part they are parallelized, but not fully parallelized. We didn't need to look into this yet because we consider semi-empirical approaches. And of course, what you can have specialized hardware for certain steps of the calculation, like the 2-electron integral calculation. So what we have focused on so far is semi-empirics for various reasons. First of all, we started out we were asking ourselves whether it's possible to have a semi-empirical model that will basically work for the whole periodic table. And so my PhD student, Tamara Husch, took care of this. She considered all these models which are around. Right? You see the time axis here, your typical names that you might have seen before. And she actually implemented all of this. It turned out nothing works. But we wrote a nice review article on this. So there are a couple of errors in the existing literature. She implemented everything. We have our own MOPAC program, including Walter Thiel's OMX methods. We will make this accessible in a few weeks with source code. And that was the result of that work, but we realized it doesn't work. Until Tamara found a paper from 1965, where at that time people tried to exploit semi-empirics to get Hartree-Fock calculations done. And so you have a mapping of the electron-electron interaction in Hartree-Fock to the NDDO, quick, fast, the NDDO evaluation of these integrals through a matrix. And in 1965, people thought that you could have a general matrix. So you train it on a couple of molecules, and then it will work all the time for any kind of molecule. And no surprise, that didn't work. But that trick works for us, because we have a continuous change of structures. We do one DFT calculation, then we learn this matrix. We use the matrix for similar structures as long as we can until we need to do a new DFT calculation. And so we call this a size approach, and that is what we are considering now. So we would do basically a semi-empirical calculation, but of DFT quality. Okay. This is our framework. We have a virtual lab to manipulate the structures. We do the manipulation with new hardware devices. You can use a mouse, of course, you can use a mouse, but it's more convenient to have an input device for 3-dimensional input. All the data is stored into a reaction network that can be further processed, because the data, so we get structures, the structures need to be refined, and also the energies need to be refined, but that can be done in an automatic way, and we then transfer this to a kinetic modeling approach. These are our first implementation, that was a pilot implementation was in the Samson program that is developed in Grenoble. And that implementation can be downloaded from the webpage of the Samson people, Samson is a molecular editor which allows you easily to write apps. And so we have an app for the exploration of structures, and we have an app that talks to our haptic device. And these are some screenshots. You see, it's a simple Dietz-Alder reaction. You manipulate only one atom. That's given here in orange. Now, if you move for ethane, this carbon atom, slowly, then the rest of the molecule will follow. And you know that the Diels-Alder reaction is actually a reaction where you form 2 bonds, but you manipulate only 1 atom. Still, you can see 2 bonds forming. If, for instance, you don't have the right orientation, right? If this part of the molecule is somewhere here, then you will see no reaction. And the pen of the haptic device will push you back. Okay, this is really a way to figure out what the reaction channel is. Well, that's it. And so we have this way in Samson to manipulate structures, and then we can map out a reaction network here. This is from 2014. We have our own implementation by now with a much more sophisticated reaction network. That's one example that we can do, that we could do already in 2014. These are many more atoms than the SN2 reaction that you have seen before. It's a natural product. It's called endiandric acid C. And it involves 3 pericyclic reactions that need to occur in order for the product to be formed. And you can do these structure manipulation interactively. So you can go through this step by step, and it's really easy for this chain-like molecule to prepare the proper configurations. It would be much more difficult to do that in a standard way. This is Moritz Haag, that is Alain Vaucher. They were the first 2 to set up this interface. We have a movie on our webpage. If you want to see this in action, I kindly refer you to their webpage, because we have a movie there. So now we can do these calculations interactively. That allows you to introduce new concepts. And one of the new concepts that we look at, we call molecular propensity. Because what I always found disappointing in quantum chemical studies is that you need to have constraints before you start. You have constraints before you start the calculation. And these constraints basically limit what you see. Like, you need to agree on the number of electrons in the system, on the charge, right? And usually you need to fix a spin state. Sometimes you don't know what the spin of the system is. Then you might look at more than one spin state. But you need to fix all these things before you can start. And of course, in the interactive system, you need to do that too. So basically, it means you explore just one Born-Oppenheimer surface. What if the system is prone to being reduced, oxidized, protonated, change spin? Okay, you wouldn't see that. But I would like to see that. Since the calculations are so fast, I can run them in parallel. And that is actually what we do. You see, this is a prototypical reaction here. It's iron oxide cation, which reacts with molecular hydrogen to form the iron cation and water. That is a reaction. We picked it not because it involves only 4 atoms, but because this is a system which led to a new concept, and that is 2-state reactivity. It was studied in the late 1990s in a mass spectrometer in Helmut Schwarz's group in Berlin. And when you do the quantum chemical calculation, you realize that the reactants are on a sextet surface and the products too. And so you explore the sextet surface and you see you have a huge barrier. So they realized immediately that kinetically it shouldn't be possible to see the reaction. Still, they saw it in the machine. And then they realized that there's a quartet state coming down, intersecting the barrier. So the system switches to the quartet surface and then back to the sextet surface. And that is how the reaction product is formed. And that is why they call it 2-state reactivity. Now we can do the same. So we start on a sextet surface, and here the computer tells you, watch out, there is a spin state coming down in energy, which could be important, right? The moment we have this structure. And here we come back. So it gives me an idea of what the system can do. And this way I can really have an in silico discovery, which I wouldn't have anticipated. And this takes just a few seconds to figure out. It took much more time to figure this out when they saw it for the first time. Here's another example. This is a Schrock complex, which is the first system that was able to reduce molecular nitrogen under ambient conditions in 2003. You see, this is an N2 unit. It has already 2 hydrogen atoms here. There's another proton coming here. Now, if I want to protonate this is my acid. I see the red curve. And you see it's bumpy, of course, because it's a manual exploration. That's why it's bumpy, right? And you see also that the barrier is extremely high. It's in kcal per mole, it's 110. Okay? But at the same time, I look at the reduced species, or the system looks at the reduced species. And when I arrive at this structure, the computer tells me, watch out, it's better to reduce your system, because then the energy stays there. And what you see here is nothing else but proton-coupled electron transfer. And actually, I was hoping for Sharon to talk about this before me. Yes, I hope that she would have liked it. So these calculations allow for true surprises. If you haven't anticipated that, the computer will tell you that something is going on. It does not need to be super accurate. You just need to know that there's a state and energy coming down. Say if it's 100 kilojoule per mole away, it's still worth exploring this in a decent calculation afterwards, right? More on immersion. I'm almost done. Of course, you have seen the haptic device, but not really the virtual reality. The virtual reality was still on a screen, right? And you would like to do more about this. And I'd like to refer to Dave Glowacki's work in Bristol, and they published a paper in Science Advances earlier this year, where they presented their setting. People carrying these head-mounted displays and then controls in their hand and can manipulate together molecular structures. In this paper, what Dave describes with his co-workers is a force field implementation. But we have also tried our quantum mechanical implementation, the semi-empirical engine, in this setting, and it works amazingly well, even if the calculations are run on some cloud server somewhere in the world. Okay, and that's pretty amazing what can be done these days. And I think that these devices, these settings will have a big future. And one of the things I would like to look into in the near future is actually Microsoft's HoloLens. Compared to these head-mounted devices, this is just a screen which allows you to see the virtual reality, but at the same time, other people to discuss science, right? And so I talked to Dave about this. Dave is not really convinced that the display is small. It works. It is really cool to try this out. I don't know whether you have had a chance to do that, but it's really cool. You see a three-dimensional representation in front of your eyes, and then the rest of it's called a mixed reality because it does not take away the reality. Okay, but as far as I know, the people at Microsoft are working at larger screens. So I think it's just a matter of time that we can have devices which will be very useful in this setting. Which brings me to my summary. So I have shown you examples that real-time electronic structure calculations are feasible. I haven't told you how we do the uncertainty quantification. So the fact that we know how wrong we are, we'll do that tomorrow. If you do real-time calculations in these new virtual environments, you can address your tactile sense. That is a way to explore the results because you simply have no time to look at alphanumerical output. It gives rise to new concepts because the data flow is so fast and the calculations are so fast. So you can look into other options that you haven't considered. So you can waste computer time because it's cheap. The availability of our program is as such. We have a prototype in Samsung, which is already available. We have our own software project where we will make everything available that we have done in the past 4 years. It's called the SIGN project. Some modules are already available. Further modules will come within the next 12 months. We also have our own graphical user interface and so on. Of course, the work wasn't done by me. It was done by the people in my group. Alain Vaucher, Tamara Husch, Moritz Haag, Adrian Mühlbach, Konrad Marti. They have worked directly on this interactive quantum chemistry project. And I'm grateful to all other members of the group because they all contribute to parts of the SIGN project. And financial support came mostly from ETH Zurich. And that's all I wanted to tell you. I thank you very much for your kind attention. Thank you very much.